Good morning, everyone. On behalf of the organizers, Professors Robert Brandenberger, Jerome Martin, Subodh, Patil, and me, let me welcome you all to the School on the Physics of the Early Universe. We had originally thought of a week-long school and a week-long workshop. We had focused on the workshop part of our plans in the online precursor that was held in August, September 2020. So we thought we'll focus on the school this time around. We are very glad that we could hold a hybrid meeting and that the participants could be physically present at ICTS. This has been possible due to the constant encouragement of Professors Rajesh Gopakumar and Abhishek Dar, and the incredible amount of administrative support provided by Ms. Aruna Mahendrakar and Ms. Anupama Murali. I would sincerely request all of you to follow protocols closely so that the school proceeds smoothly without any distractions. Let me now request my co-organizer, Professor Jerome Martin, who is joining from Institute of Astrophysics, Paris, to say a few words about the scientific program of the school and also introduce our first lecturer for today, Professor David Wants. Over to you, Jerome.
So let me welcome you all once again on behalf of the organizers. So the aim of the school is to introduce graduate students and postdoctoral fellows to essential ideas and recent developments related to the physics of the early universe. The school will begin with lecture on cosmological perturbation theory and alternative paradigms, such as inflation and the bouncing scenarios for the generation of the primordial perturbations. They will be followed by lectures on the relation between models of the early universe and particle physics, as well as comparison of these models with the available and forthcoming cosmological data. These lectures will be complemented with lectures on topics of considerable interest today, such as the nature of dark matter and dark energy, and the generation of the gravitational waves in the early universe and their observational imprints. So during this school, we have David Wants from the University of Portsmouth, England, speaking about cosmological perturbation theory. We have Will Kinev from the University of Buffalo in the US, speaking about the inflationary paradigm. Patrick Peter from the Institute for Astrophysics in Paris, France, speaking about the bouncing scenario. Masaide Yamaguchi from Tokyo Institute of Technology, Japan, speaking about particle physics in the early universe. Shiv Sethi from Raman Research Institute, India, speaking about comparison of models of the early universe with the cosmological data. Daniel Figueroa from the University of Valencia in Spain, speaking about generation and imprints of primordial gravitational waves. Kathleen Schutz from McGill University, Canada, speaking about dark matter. And finally, Alessandra Silvestri from Leiden University in the Netherlands, speaking about dark energy and modified gravity. So we hope that you interact with the lecturer as well as the participants and derive the maximal benefit from this school. So I would now invite Professor David Wants to give the first lecture at the school. Before I hand over to David, let me briefly introduce him. David is a professor of cosmology and director of the Institute of Cosmology and Gravitation at the University of Portsmouth. David has worked extensively on a variety of issues related to the physics of the early universe, ranging from inflation, cosmological perturbation theory, alternatives to inflation, post-inflationary dynamics, and stochastic inflation, to name just a few. So as I mentioned, at this school, he will be lecturing on cosmological perturbation theory. So David, if you can hear me, I guess the stage is yours.
Okay, thank you very much, Jerome. I hope you can all hear me clearly. It's a pleasure to be here online. It's a shame I cannot be with you in person as we'd originally planned, but new times and perhaps new opportunities to do things differently. And it's great to have the opportunity to address so many people online. And if I share my screen with you, I will, let's see. Hope you will be able to see the title slides for my talk. And so I'm going to talk in my lectures about cosmological perturbation theory. So if I start with a general outline of what I'm going to cover today, I'm going to start with some general motivation and an introduction to the topic as the first lecture here on the physics of the early universe. So I will give some of the observations that motivate us to study not just the simplest homogeneous and uniformly expanding cosmology, but a realistic cosmology with variations in the distribution of matter and therefore in the space-time that we see around us. So I'll touch a little bit on the observations just as the motivation for why it is that we study inhomogeneous perturbations in cosmology. And then I'll really get into defining the basic building blocks that we'll use in the rest of the lectures to discuss the inhomogeneities in our universe. So indeed, we start with the background of in the very early universe, to a good approximation, there is a homogeneous expanding universe from what we see from observations. But then we'll study the fluctuations, the perturbations about that background, and in particular, how the fluctuations in the matter are reflected in the fluctuations in the geometry of space-time, and I'll represent those as metric perturbations in the universe. Okay, so I will, as I say, start with the big picture. So I will be the first in the school to show you this kind of picture, the image we have of really the history of our universe and how it explores the physics at play at different energy scales, indeed, in the universe, from the various earliest times that we can model, a fraction of a second after the hot Big Bang, through until the present day, and the low energy universe that we see. So in this picture, produced by the Particle Data Group collaboration based in Berkeley, California, we see a range of epochs in the history of our universe. As I say, this is how our early universe explores physics at play at different epochs in the expanding hot Big Bang cosmology. And some of the key epochs highlighted here are, and the sort of key pieces of evidence originally for the hot Big Bang come from, well, of course, in the middle here, 300,000–400,000 years after the hot Big Bang, we see the radiation of the cosmic microwave background when electrons and protons recombine. So by studying atomic physics at this epoch, we can understand that there was a hot plasma at higher temperatures, higher densities at earlier times. After this epoch of last scattering of the cosmic microwave background radiation, the universe becomes transparent to electromagnetic radiation. And so we see this radiation from this last scattering surface, and the discovery of the cosmic microwave background radiation in the 1960s, really for most cosmologists, was the clinching evidence in favor of this hot Big Bang model of the early universe. There had already been indications of the redshift dependence of the properties of galaxies, and indeed now we talk about the changing properties of the stellar star formation history of galaxies at later times in the universe. And then, of course, back at earlier times, at the first few minutes after the hot Big Bang, we see the temperatures and energies high enough to fuse produce the lightest atomic nuclei. So this epoch of primordial nuclear synthesis, temperatures about 1 billion Kelvin, but well understood nuclear physics that allows us to predict the primordial abundance of the very lightest elements, in particular the ratio of hydrogen to helium that is seen in the high redshift primordial gas clouds. So these are the sort of key aspects of the hot Big Bang model, and the original back through through the 1960s, 70s, and 80s provided the cornerstone evidence for the basic picture of an expanding universe starting in a hot Big Bang. The sort of epochs that are really crucial to the modern precision cosmology, where we really are able to make very precise measurements of the parameters of this primordial hot Big Bang cosmology, are again this epoch of the cosmic microwave background last scattering. So we see not just now the average temperature thermal radiation from the hot Big Bang, but really detailed information about the temperature and anisotropies and indeed polarization power spectrum of the radiation emitted from this surface. And increasingly, as we look to the future, we look to the detailed structure seen in galaxy surveys. And especially in terms of learning about the early universe, we're very interested in seeing the primordial structure that exists on large scales in the high redshift galaxy surveys, astronomical surveys now mapping the distribution of galaxies around us. So just to look in a little bit more detail at those two key pieces of information, if we look at the cosmic microwave background, well, as originally discovered in 1965 by Penzias and Wilson, this is really a remarkably uniform thermal radiation, just 3 degrees above absolute zero, 3 Kelvin. This radiation in all directions around us was this residual noise, this background radiation in their telescope, which it was realized by people like Peebles and Dickey at Princeton University was exactly the relic radiation from that hot Big Bang plasma predicted in the expanding hot Big Bang cosmology. But it took almost 30 years to be able to go beyond this uniform picture of uniform radiation being emitted in the early universe. And it was in the 1990s when I was doing as I was finishing my PhD that the results from the NASA's COBE satellite came out with the first evidence for some level, faint level of anisotropies, that is, variations in different directions of the temperature. And this was seen at the level of just a few tens of microkelvin, so a few parts in 100,000, we begin to see primordial structure. Not this blazing red pattern along the central band here, if you can see the pointer here on my screen. That's our galaxy. But away from our galaxy at high galactic latitudes, you begin to see something more than just experimental noise, some intrinsic variation in the temperature seen in different directions in the universe. And that was revealed with dramatic detail in the 2000s, first by the WMAP satellite here, the NASA satellite, really producing detailed picture of the primordial anisotropies at the one degree level, and seeing this characteristic scale of temperature fluctuations. And then most recently with European Space Agency Planck satellite, which now has this, gives us this fantastic view of the universe 300,000 years after the hot Big Bang. And really, this is now so well modeled that we can extract the galactic emission, which, if you remember, is there as a foreground to looking out into the cosmos to see the emission really from the early universe. We can model that well enough to subtract that and get this picture of the temperature variations really across the whole sky. Still, as you see, just a few tens of microkelvin fluctuations typically across the sky. Typically on this, you see the typical scale of these fluctuations at about 1 degree. Planck also mapped with higher resolution, not just the temperature, but also the polarization of the light that's being emitted. And this maps very well with the polarization that we expect to see partly from the radiation as it's emitted at the last scattering surface, also as it's rescattered along the line of sight by the reionization of ionized gas clouds at lower redshift. And we really get from this a lot of detailed information to compare with our theoretical models. And these are the sort of remarkable plots that you can see of the, in red, the measured temperature power spectrum against some of the theoretical curves. Here, these are the predictions of the hot Big Bang cosmology, the standard concordance type cosmology models, with the dark matter, the dark energy that you'll have heard of dominating the energy density of the universe today, but also crucially the baryonic matter, the matter of which we're made of, as it scatters with the electrons, with the photons, and produces these characteristic acoustic peaks. And here we see in the top graph of the temperature angular power spectrum, this peak at the 1 degree angular scale, but also reflected in similar patterns of acoustic peaks in the polarization and indeed the temperature polarization cross correlation power spectrum in the center here. There's even a picture here of the lensing along the line of sight, the gravitational lensing of the micro background radiation due to the clustering of matter along the line of sight. And that's shown in this really remarkable map produced by the Planck satellite, not just of the intrinsic fluctuations at the last scattering surface, but mapping how that's distorted. We can model this so well in terms of the effect of lensing along the line of sight by structuring our universe, which distorts the space-time geometry, and then therefore the gravitational potential gives this lensing effect in different directions along the line of sight. It distorts the angular scales in different patches of the sky, and that's recreated, can be modeled, and therefore the intervening lensing potential along the line of sight is shown in this all sky map produced by the Planck satellite. So I just wanted to sort of emphasize really what's going on here is when we compare theory with data, you see that, of course, the data, the universe we see has a very specific pattern of temperature anisotropies. These really reflect, in fact, in blue here, what we're seeing are overdensities on the last scattering surface, gravitational potential wells. The red spots here are underdensities on the last scattering surface. And of course, our universe, our last scattering surface has a particular specific pattern of hot and cold spots. And our theoretical models don't predict precisely which directions are hot and which directions are cold. But what we can do is understand, as far as we know, those are intrinsically random. But what we can see is properties, statistical properties of the map. In particular, as I say, the angular scale. You see that there, we actually see by eye the characteristic size to the hot and cold spots on the last scattering surface. And those are the properties that we predict by the theory. So we predict the average temperature fluctuations on a scale rather than in a particular direction. And so that's the comparison that's being made here in these graphs of we reduce in the top graph, this is the temperature power spectrum. So it's not the temperature in any particular direction, but it's the temperature as a function of angular scale. Actually, you can see the x-axis here is in terms of multipoles, but on the left-hand side, the second multipole, for instance, is a quadrupolar variation across the sky. So on the 90-degree scale variations, but by the time we get down to a few hundred multiples of 1 or 200, these are angular scales of around a degree scale, and then we get down to sub-degree scales on the right here, where you see the power decays away. So these are the blue curves here is a theoretical prediction. It's from a numerical model of the anisotropies, but with only half a dozen basic parameters to describe the cosmological model. And by constraining, comparing these theoretical predictions against the data points, we're able to, we call this an era of precision cosmology, because the fundamental cosmological parameters, the relative densities of the different dark matter and dark energy components are constrained to about 1% level by these kinds of observations. So as I say, it's the statistical nature that we'll discuss in my lectures. I'll be talking about the theoretical properties, and there we're discussing the properties of the statistical distribution, quantities such as the power spectrum, not the detailed structure of any particular map of the cosmic microwave background sky in any particular direction. And indeed, the data from Planck, shown in dark blue here, is now extended down to smaller scales by later ground-based experiments still in progress, such as ACT and BICEP, taking data in the South Pole, in the Atacama Desert, dry places on Earth, where they taking now mapping at higher resolution, especially extending the information on the polarization and isotropies on small angular scales here. So this builds up a coherent picture of this distinctive structure and power spectrum. And so as theorists, we need to understand where this primordial structure comes from that we see even in the cosmic microwave background radiation. Increasingly in the future, that sort of detailed information is going to be augmented by mapping the distribution of galaxies around us in the universe, and therefore the present matter density in the universe. And this is the ambition of galaxy redshift surveys. One of the most influential surveys over the past 10, 15 years has been the Sloan Digital Sky Survey, which recently completed its the fourth incarnation of the Sloan Digital Sky Survey, mapping several million galaxies, the three-dimensional position. And these galaxies, if we think of a wedge of our universe here, where we're located in this bottom right corner, observing at the edge of our observable universe is the cosmic microwave background radiation that we've just seen. This is just a two-dimensional surface. The galaxy surveys have the potential to map the three-dimensional distribution of matter. And currently that's distributed around us, billions now, increasingly mapping out to billions of light years distant from us, out into the universe. Indeed, there's ambitions to map even the high redshift gas distribution in radio surveys out in the universe around us. The sort of picture, the state of the art currently is this kind of map from the EBOS galaxy and indeed quasar survey completed in 2020 by the Sloan Digital Sky Survey. And you see here as they look back out into billions of years out into the universe around us. So as they say, of course, this is a look back time of 5, 10, 12 billion years out into the cosmos. You see different populations of galaxies. This really reflects the sensitivity of the telescopes, as well as the intrinsic distribution of galaxies as at different redshifts at different stages in the universe. And indeed, if you can see here on the right-hand side, even in the distribution of galaxies now, one of the key signals of the hot Big Bang cosmology is seen here again. These characteristic acoustic oscillations in which we saw in the distribution of light from the cosmic microwave background. There's a characteristic scale imprinted by the existence of primordial density perturbations, the oscillations of the primordial plasma. They're imprinted in the cosmic microwave background radiation, and we see the same characteristic scale imprinted in the distribution of galaxies here. This is the so-called baryon acoustic oscillations seen in the distribution of galaxies. It's more weak in the distribution of galaxies because their distribution is dominated by dark matter, which did not participate in those acoustic oscillations in the primordial plasma. But the baryons are present. They imprint it in the distribution of matter, and it's seen in the distribution of galaxies. These are on large scales in the universe around us, and indeed, the mapping that scale at different redshifts, seen here in the different galaxy population types, from nearby galaxies in green here, luminous red galaxies in red and magenta, out into more active young blue star-forming galaxies, and indeed in the distribution of active galactic nuclei and quasars at much higher redshift. We see that characteristic scale imprinted at several redshifts, and how that evolves in time is one of the key ways in which these surveys and the structure in these surveys is used to probe dark energy in the universe. So these galaxy surveys there's a whole series of program of galaxy surveys coming up in the next decade, which will produce more detailed maps of structure in the galaxy surveys. We can use that to probe the current universe, but the hope is we will also can use it to learn about the primordial structure, detailed information about cosmological perturbations at high redshift. And again, it's not the specific distribution and positions of galaxies, it's the statistical power at different angular scales that we see here, both in galaxy surveys, and then, so this is done in terms of the wave number, that's the inverse of the wavelength that we probe from megaparsecs up to hundreds of megaparsecs in these galaxy surveys. And on the left-hand side, we see how it connects with the primordial structure in the cosmic microwave background at thousands of megaparsec scale, gigaparsec scales. And the picture we have is that from the primordial structure in the cosmic microwave background radiation, it's through the gravitational instability that the matter clusters into the large-scale distribution of galaxies in our universe. And as I was saying, we use this to test both the composition of the cosmos and the nature of those primordial perturbations in the very early universe, and therefore learn about the physics that's operating at scales even beyond those that we can test in terrestrial experiments. So the picture we have of the composition of the cosmos is what we see here. The universe dominated today, 70% of the energy density of the universe today in dark energy, 25% in dark matter, that is matter that does not interact significantly with light. So it's out there as dark particles in the universe around us, and only about 5% of the matter content of the universe today is in the baryonic matter, the atoms, and that we see primarily indeed in hydrogen and helium, but to a lesser extent in the heavy elements, what the astronomers call metals, anything really beyond the lightest elements, some neutrinos, and a small fraction of photons today, a small fraction today, but it's those photons that we see in the cosmic microwave background that dominate the density of the universe at early times. So that's the motivation for studying the structure in the universe. The key questions which then we'll try and address in this course is, well, the fundamental question I'll be talking about is how to characterize these inhomogeneous structures that we see all around us, really at all scales in the universe. So they're inhomogeneous in the sense that the density varies in space, but of course, as we see, it also evolves in time around us. So to do that, we'll discuss, first of all, briefly, the homogeneous background cosmological model that we use, but then we're really going to study the nature of fluctuations about that background. So we perturb that background, and we'll do that in the context of Einstein's theory of general relativity. And through that, studying that, the questions that we can go on to ask is how we can probe, well, the history of our universe, in particular through this large-scale structure, but also how, where that primordial structure originates. And that's where we're looking to models such as inflation or perhaps to alternative models for the origin of these fluctuations. I'm going to talk about the basic building blocks really for studying these inhomogeneous cosmologies. Before I do that, are there any general questions about what I've been saying so far? Can you hear clearly what I'm saying? The slides are changing, I hope.
Yeah, David, there are a couple of hands here. I will just let the participants ask the questions.
Hi, David. I had a question regarding your slide on the angular power spectrum of the CMB.
Yeah.
Yeah. So I was just wondering, sorry if this is a naive question, but why are the error bars in the lower multiples higher and the error bars on the higher multiples, practically not there?
Yes. So that's a good question, and sometimes what's done in the theory in introducing these errors is estimating these errors is that there's an uncertainty due to cosmic variance, which we call cosmic variance in now this is really an uncertainty in some sense in the the predictions as much as in the experiment, because because these low multipoles, say the quadrupole, there's only 3 orientations of that that we can observe. So whereas on the small scales, there are many multipoles. So each of these multipoles, so the x-axis here is the multipole L, and there are 2L plus, there's 2L plus 1 realizations of that we see on our sky. So if you ask the question as to what power there is on the 1 angular degree scale, of course, there are many 1 angular degree patches you can look at to make that estimation. And this is so the experiment then estimates the average power on a 1 degree scale. And we have several hundred estimates of that from which to get a small error bar here on the 1 angular degree scale. But if you're looking up at the lowest multipoles, you're really looking at 90 degree scales. And then there's basically only 3 ways you can sample that in this 360 degree map. So there's a larger error in our intrinsic estimate of the power on that scale. Sometimes that's represented as a spread in the theoretical curve, and sometimes that's included in the experimental data points, the estimates so you might see it represented in either way. I think that's as you in this particular power spectrum, I'm now not entirely sure, but I think that's probably where you see this general rise in the estimate of the power spectrum, the experimental estimate of the power spectrum on large scales here.
I see. Thank you. I think I understand. Thank you.
Are there any other questions? There are no more questions here. David.
Thank you. Okay, I shall. So I wanted to show some the general motivation. What I'm going to do next is to really get into some of the real details here that I go through in the course. I should mention as well some of the references here. I realize I won't give so many references as I go through the different introduce specific points. I'll do it in my own way. But a lot of what I'm talking about, certainly when we start talking about metric perturbations, really goes back to a classic paper by Bardeen in 1980, when he really began set out how to construct gauge invariant perturbations in cosmology. And there's a really nice review by Kodama and Sasaki from 84, and they really extend that to introduce define not just the metric perturbations, but also the matter perturbations in a gauge invariant fashion. There's a paper by one of our organizers, Robert Brandenberger, with Slava Mukhanov and Hume Feldman in 1992, was hugely influential, and in particular sets out a nice structured way to calculate perturbations from inflation that was now being realized as being the offering a concrete model for the origin of perturbations. And that's developed and extended beyond linear perturbation theory in a review I wrote with Karim Malik in 2009. So if you want to find, you'll have access to all these slides, but if you want to go back and look back at the papers that a lot of these results come from, these are some of the classic papers you can look at. So as I say, briefly, let's just remember that we're going to work in the context of general relativity. This can certainly be extended to other theories of gravity, but what I'm talking about really is going to be modeling gravity through the space-time metric. So this is a description of the curvature of space-time, and this nice simple idea of general relativity, often more complex to realize and solve in practice, is that it's really the curvature of space-time that tells matter how to move. So the matter follows, often we'll see non-relativistic matter follows geodesics in this curved space-time, but it is the distribution of matter itself that produces that curvature of space-time. So we'll model both of these effects through general relativity, and as say, you can extend that into modified gravity theories. That's a particular interest at the current time, but most of these incorporate and build upon, add to the basic metric description that we see in general relativity. So we start by modeling that curvature of space-time using this picture of cosmology, first derived by Alexander Friedmann, not long after general relativity was first proposed. He realized that there were dynamical solutions in cosmology, and the way we write that these days is in terms of a space-time where which is uniform in space. So we have, in fact, maximally symmetric three-dimensional surfaces at any fixed time, but those surfaces, three-dimensional hypersurfaces, grow with time, and grow, we describe that, all of the dynamics of space-time is described by a single scale factor, A of t. So it's a four-dimensional space-time, but it naturally, there's a natural split into a three-dimensional space, and the product of that with time, and there's just an overall evolving scale factor. So I'm going to write that, and we write that in terms of the Friedmann-Lemaitre-Robertson-Walker line element. So ds squared here, and with my sign convention, will be minus the speed of light, c squared, times the time interval dt squared, plus the spatial interval dx squared multiplied, as I said, at each time that's multiplied by the scale factor A of t. So we've got time plus a homogeneous and isotropic three-dimensional space, and with an overall scale factor dependent on time A of t. And that space can, in principle, be any maximally symmetric three space. So you could have a curvature K, which is positive, negative, or zero. And so I can't draw three-dimensional space, but here's a picture of two-dimensional spaces with positive, negative, or zero curvature. So spherical, hyperbolic, or flat space. These are all uniform at all points in space with a uniform curvature K. Fortunately, in our universe, in terms of simplicity, it's sufficient to describe all those observations that I've shown, those theoretical predictions I've shown for the cosmic microwave background, for example, also for the distribution of matter, is modeled within a flat spatial geometry and the perturbations about that. So we will, unless as otherwise stated, I'll work with flat space, which keeps life simple. It might be more interesting if there is some underlying curvature, and it's certainly possible that there could be some degree of curvature in our universe, perhaps at the percent level. Indeed, it can be argued that there must be, in our observable universe, perhaps the nature of inflationary fluctuations, for example, would give us some small level of curvature. But at the moment, it's effectively too small to be detected in the current data. So we'll work with a a flat background space-time. We'll sometimes it's convenient to use a slightly different time coordinate from the naive time coordinate t that I was talking about before, that was just the proper time measured by observers. Sometimes it's useful to rescale the time coordinate in much the same way that we rescale the physical spatial coordinates. We've got, we call x here the spatial co-moving coordinate x, and then we multiply it by the scale factor t to get the physical scale at any given time. We can do the same with the time coordinate. So in effect, we're taking out a factor of taking this scale factor, factorizing that out of the time coordinate as well. And then this coordinate tau is what we'd call the conformal time coordinate, because the line element is then just a conformal factor, a squared, times the line element of flat space time. And that's a useful, often mathematically useful, because you can see here that in this line element, light travels along null light rays, that is the displacement ds is zero for light rays, and so tau is basically measuring the co-moving distance traveled by light. So in the tau and x coordinates, light is traveling at 45 degrees here. So tau is really telling us about the distance traveled by light, co-moving distance traveled by light, and that's what we would call the horizon distance in our universe. Either a particle horizon, how far light can have traveled since the hot Big Bang, or as we'll see in an inflationary universe, we get instead an event horizon where light can only travel finite co-moving distance into the infinite future. Both of these sort of horizons are characterized by this conformal time coordinate. And that also provides a useful point at which to introduce, to simplify the units that we're going to use. For example, when we look at the line element, if we're using spatial coordinates x or a times dx, and comparing that with a time interval dt, then of course to convert between time and space, in these line elements, we're always multiplying by the speed of light. And really in Einstein's theory, we should think of time and space as just coordinates within the space-time. And it's really just almost a convention that time has different units from space, and the conversion factor is c. So in natural units, one might measure time and space in the same units. In fact, astronomers often measure conformal time indeed in gigaparsecs or megaparsecs. So in talking about time and space as having the same units, we're effectively setting c, the speed of light, to 1. And that's an example of natural units that theoretical cosmologists like me like to use to simplify the equations that we use. So we'll set c to 1. We'll often set the Boltzmann constant to 1, because temperature, we think of temperature as being equivalent to a particular thermal energy, the Boltzmann constant times the temperature. So temperature and energy can be the same units. And we'll set the Planck constant h bar to 1. So angular frequency of a photon immediately tells us the energy of a photon. So if we set h bar to 1, we're effectively thinking about frequency and energy and mass and temperature all as being just representations of the same fundamental units. So the only fundamental constant that I will leave throughout is Newton's constant g, and then the fundamental units are really the natural units are really what we call the Planck units, and we'll keep track of that through Newton's constant g here. So if you wonder where the speed of light has gone, or the other fundamental constants, it's because I'll be using natural units most of the time in the description here. Okay, so for example, if we then look at the dynamics of the and Einstein's equations for the dynamics of this scale factor A of t in Friedmann's cosmology, we're talking about the rate of change of the scale factor A dot over A, and that is just the Hubble expansion rate in this uniform cosmology. H naught, of course, is, well, about 70 kilometers per second per megaparsec. That's one of the targets of modern observational cosmology, is still to pin down the precise value of that. The uncertainty means that we're often use this, you may often see this small h factor introduced as an uncertainty to reflect our uncertainty in the actual current value of h naught. So instead, we can talk about h naught as being 100 little h kilometers per second per megaparsec. But you should think of little h here as being 0.4 or so. And that in Einstein's general relativity, if we have this very symmetric space-time with a scale factor A of t, all the complexity of Einstein's equations for the curvature of space-time reduce really to this simple equation, the Friedmann equation here, for the rate of change of that scale factor. So the Hubble rate, and the Hubble rate squared, is given in terms of the energy density at any time in the universe. So, and in particular, it's 8 pi g, Newton's constant, over 3 times the energy density if at any given time in the history of the universe. And of course, naturally that changes with time. The continuity equation tells us how the density of matter changes in an expanding universe. So we can model different expansion histories from radiation dominated, matter dominated, or more exotic forms of matter in the universe through this Friedmann equation. Of course, you may know that there's also a term in this Friedmann equation possible in general relativity to include a constant in the action from which the dynamics of general relativity is derived, and that shows up as a cosmological constant in this Friedmann equation. So lambda appears here as a constant term, equivalent really just to a constant energy density. So it might naturally arise as some kind of vacuum energy density in the universe. It might play a key role in models such as inflation in the very early universe, but in recent years, we've realized that it also plays a role at what's actually very low densities, so unexpected in that sense, an unexpected role at low densities, taking over, beginning to dominate the expansion of the universe today. Finally, so there's this curvature term in general in these Friedmann models of cosmology, but there's no evidence for this playing a role in the universe today. So it could be there. And the fractional contributions of these three terms are typically represented in terms of this capital omega. So if you divide through by h squared, you get this dimensionless version of the equation, which says that the total expansion rate in dimensionless units is 1, and that's driven by the matter density. Today, this is about 0.3. The cosmological constant, today, this is about 0.7. And the curvature, which today is less than about 0.01. Finally, then, having set up the standard cosmological background, we want to study perturbations. So we actually want to study the fluctuations around that smooth, homogeneous background space-time. So we're going to break that uniformity of the Friedmann cosmology. And because we see variations in the density, the pressure of galaxies around us in the universe today, but also even in the early universe at the small level, at the 1 part in 100,000 level, we see variations in the density and pressure of that primordial plasma reflected in the anisotropies of the cosmic microwave background. And so we need to spoil that, but if we were to really solve the full nonlinear numerical solutions of general relativity with a relativistic plasma, that's a challenging problem once we lose the symmetry of the homogeneous, spatially homogeneous background space-time. And any numerical solutions are going to have a limited dynamical range if we're trying to model the full nonlinear complexity. And this is where we use instead perturbation theory. Perturbation theory is based on assuming that these fluctuations are small. And that's a good approximation, we believe, in the very early universe, certainly. And we believe that's still a good approximation in the late time in our present universe, at late times, at least on large scales. We know it's not a good approximation in this lecture room. Things are very inhomogeneous here, but in the very large scales in the universe today, or as we go back in time, at very early times in the universe, these inhomogeneities are small. So what we do is we introduce a small fluctuations, and by assuming the fluctuations are small, in the simplest case, we can indeed only introduce, keep the linear fluctuations, and that allows us to make analytic progress to some extent. But even when we're looking numerically, it gives us a much wider dynamical range. It's much easier to solve linear equations. And then indeed, we can study the nonlinear complexity, but in a perturbative fashion by building up the nonlinear behavior starting from the linear perturbations. I'll show you what I mean by that, I hope, in what follows. So what we're going to do is we're going to take a scalar quantity to start off with, such as the energy density rho, and we study the behavior of this at a fixed point p. So this is at some coordinates t and x in this dynamical cosmology. But in perturbation theory, we model that as having a spatially uniform part, rho bar here, and of perturbation delta rho. And if delta rho is small, it's useful to model that as being as a perturbative expansion. And that's an expansion in this small parameter epsilon here. So we model delta rho as being, first of all, at order epsilon, it's a first order fluctuation. I'll call that delta 1 rho. And then there are further more complicated dynamics associated with higher order terms. First of all, there's a term epsilon squared times delta 2 of rho. And similarly, there'll be a term epsilon cubed and higher order terms here. And it might, of course, seem a bit, so you can hopefully see why it's useful to split rho into rho bar plus delta rho, because rho bar is homogeneous and large, and delta rho is inhomogeneous but small. It might be less obvious why we then split delta rho into further parts, delta 1, delta 2, etc. But the reason we're doing that is because the first order part is going to have this simple behavior. We're going to get linear equations for the first order part, and that means it's going to be, we can solve basically for the first order part, and then will deal with the complexity of nonlinearity through these higher order terms. And we can do that consistently and keep track of that consistently with this order parameter epsilon. Okay, so often we will be interested in, much of the discussion will be about just the linear evolution. So implicitly, when we talk about the perturbations, we're often talking about the linear perturbations. We're just talking about, which after all are the leading part. If epsilon is small, then these higher order terms would be small. But technically, we should realize that the linear perturbation is not the entire inhomogeneous, it's just the first part in it. But nonetheless, it will have the simple behavior, and the complexity of the nonlinear evolution will be restricted to these higher order terms, and we can deal with them separately. So let me try and really spell out how that works in a simple equation, simple but nonlinear equation, such as the continuity equation. And let's, at this stage, just to warm up, let's deal with a non-relativistic, a sort of Newtonian continuity equation for the energy density rho. So in Newtonian fluids, that would evolve due to the, in a simple model here, the density d rho by dt would just be given by the divergence of the flow of the fluid, rho times the velocity v. But of course, if we've got rho times v, this is already a nonlinear equation. And of course, v itself will have the Euler equation will tell us about the evolution of the velocity. So we'd have another equation to follow for the evolution of the velocity, and then multiplied by the density. That gives us a more complicated evolution for the density itself here. But we make things simple by expanding the density and velocity in this way as a background, and I'll consider the case where the background is just a completely uniform density with zero velocity. So there's so rho has this background term rho bar that's independent, that's homogeneous, and then a first order perturbation epsilon times delta 1 of rho, then the epsilon squared term. Velocity has no background term, but just a first order velocity perturbation, epsilon plus an epsilon squared term, and so on. And then we substitute these into the continuity equation, the nonlinear continuity equation. So we get d by dt of rho is given, as I said, by the divergence of the total density times the total velocity here. And the idea in this systematic expansion in perturbation theory is that we're going to arrange these terms, or now of course we have many terms in the equation, but we can collect them and arrange them in terms of their order in epsilon. So you can see that there's in the first term, of course, we've got the background, the epsilon to the 0th term, the epsilon term, the epsilon squared term, and in this rho times the velocity, we can similarly collect the terms there. So here we are. If we expand out the bracket, basically in the second term, we can get the background term, and of course the background has no velocity flow, it's just a uniform density, so d by dt of rho bar, and then we have the terms involving epsilon, and there's just two terms here, and then we've got the epsilon squared term, where we begin to get more and more terms as we expand out the bracket, and at epsilon cubed and higher orders, there'd be even more terms here. But if this is to hold for any value of the order parameter epsilon, then it should hold, these equations should hold order by order. So this equation needs to be 0 at every term in epsilon. So that allows us to solve, first of all, the background equation, d by dt of rho bar is 0. So the background always has the simplest equation. Here, it would just be a constant uniform density. Then we get the first order equation. And here in the first order equation, which comes from this first bracketed term here, we've got d by dt of delta 1 rho, so d by dt of the inhomogeneous density. But the divergence of the background density times delta v, well, we have a solution now for the background density. So perturbations, we're always solving for the first order perturbation here, where we already have solved for the background rho bar. Here, rho bar is just a constant. So in fact, this term here is not, it's a known constant now, or a given constant c times the divergence of the velocity. And so this would be the linear perturbation equation, continuity equation. It would tell us that the time derivative of the perturbed density is actually the background density times the divergence of the perturbed velocity. And so we've got a linear equation to solve for the inhomogeneous perturbations of the density and velocity. So often this is the leading order, gives us the leading order description of what the perturbations are doing. We can then use that as an input into the second order and higher order perturbation theory. So if you look at the epsilon squared equation, we've got to solve this bracket being 0. And the typical structure you see here is that actually you get the same characteristic linear operator, d by dt plus c times the divergence of the velocity, the same linear operator acting now on the second order perturbation, delta rho and delta v. But there's now a source term for that linear equation, and that here is quadratic in the first order perturbations. And if you were solving this for epsilon cubed, you'd get the same linear operator acting on the third order perturbation, delta 3 rho and delta 3 v, but you'd get a source term which was cubic in the first order perturbations on the right hand side. So so this is how, so we can build up the higher order perturbation theory from our knowledge of the solutions to the first order perturbation theory. And so this is a perturbative expansion in which we build up the complexity of the solutions. If I don't, I may say this later on in the slides, but let me just draw attention to the other reason that we do this split into first order and then higher order perturbations is that because these first order perturbations obey linear equations, we will choose to define the first order perturbations. We will describe them by Gaussian perturbations. And if delta rho is a Gaussian, then of course it's consistent that delta v at first order will be a Gaussian. But you also see that while we can do that in the linear theory, that then at higher order, the higher order terms, because they've got a source term which is quadratic in the first order of terms, the statistics of this source term, it's a product of a Gaussians, it won't itself be a Gaussian. So the higher order perturbation theory, we're beginning to explore the we inevitably have to, we're introducing non-Gaussian properties of the distribution. So this is, so at one level, this is a mathematical convenience to introduce the first order perturbations as a Gaussian. I mean, you might do it, traditionally astronomers did this because well, they just didn't know what the primordial statistics of the primordial perturbations would be. So the simplest thing is to assume that they're a Gaussian. You can do that at first order, and then you study non-Gaussianity at second order. But the increasingly motivated by ideas such as inflation, or indeed other alternative bouncing cosmological models, any model where the perturbations originate as quantum fluctuations of a field, then in fact what we're doing in the first order theory is we're studying the fluctuations of the free field. And so when you quantize the free fluctuations of the field, you naturally get Gaussian statistics for fluctuations about the ground state of the quantum field. And so the first order fluctuations are naturally Gaussian. The second order perturbations are naturally where you're discussing the non-Gaussian, the interactions of the free field, and that gives rise to non-Gaussian perturbations. So you'll see that more as we in the context of the inflationary and other models for the origin of structure. So, well, again, I could pause maybe for a moment if there's any questions just about what we're doing here as we construct the linear and second order perturbations.
Yeah, David.
Yeah.
Yep. Just turn it on and wait for a couple of seconds.
Hello.
Yes.
Hello. So you said that the background density is constant, right? But initially we assume that it is time dependent.
Yeah. So I've perhaps oversimplified a little bit here. To give this example, in the perturbation theory, I was deciding to work with a static background, a non-relativistic theory here. So I haven't got any background expansion at this point. Is that your question? So in the expanding cosmology, indeed, I would get a time-dependent background, but I've made my life even simpler here by just considering a static background initially here. Yeah.
Any other questions? Maybe, David, you can proceed and we can come back to the question.
Yeah.
Questions
we can have time later to do that. Yeah. So the next step, the next sort of basic concept just to define that we're going to use here in studying these fluctuations now. So we want to study inhomogeneous fluctuations, and therefore if we're studying the variation of density, pressure in the primordial plasma, it's often a useful way in physics to think about the fluctuations, not so much in terms of how the pressure varies as a function of the spatial coordinate x, but but to describe that spatial variation with x as a sinusoidal fluctuation with a characteristic wavelength lambda, or equivalently a wave number k. So what we're doing in that case is thinking about the fluctuations as fluctuations as a Fourier mode. So that's what I've drawn here, where delta rho and its variation in time and space, t and x, can instead be represented as actually an integral, or in a finite box, it would be a sum over different wavelengths. Each wavelength is associated with a wave vector k. So k here is 2 pi divided by the wavelength lambda. And it is a wave that varies in a particular direction. So actually, we're thinking about summing or integrating over all the possible wave vectors. So k is a wave vector whose magnitude is the wave number k, but it can vary in three-dimensional space in all possible directions as well. So we're integrating over all possible waves, and we do this we use a complex representation. So e to the I kx, this is really cosine kx plus I, the square root of -1 times sine kx, and with a complex amplitude delta rho associated with every wave vector k. And that amplitude, the amplitude of each wave is allowed to vary in time, because we'll see that as we saw in the cosmic microwave background, for example, we saw characteristic scales represented in the distribution of temperature on the last scattering surface. So we'll see that the evolution of the density varies with scale, and so it's useful to model the time dependence of the fluctuations as the time dependence of wavelengths with a given wave vector k. Okay, so this is the Fourier representation of the inhomogeneous density. So in this case, the equations can be, when we substitute this Fourier integral into the equations for the evolution of the density delta rho, then instead we get equations for the time dependence of the amplitude of the delta rho k, the Fourier amplitude of the density perturbation with a given scale wave number k. So these sinusoidal waves help us to simplify the equations. For example, if we look at the spatial Laplacian acting on the second spatial derivative operator acting on a wave, we simply get minus k squared times the wave. So we can replace these spatial derivative operators with just k or k squared here. So they're simple, they're eigenfunctions of the spatial Laplacian, and they're orthonormal, which means that they're independent. They form a basis, and they're independent basis vectors. So we can describe in particular when we substitute this in this Fourier decomposition into the linear equations for the perturbation delta rho, we get separate equations we can solve separately for each of the different wave vectors k, and the evolution in each direction with each wavelength is independent. And it also allows us to invert the transformation. So we can both extract the amplitude of the Fourier coefficient delta rho k from integrating the inhomogeneous in space delta rho against e to the minus I kx, or conversely, we can reconstruct the full inhomogeneous delta rho as a function of x by integrating over delta rho of k. So these are the essential properties of the Fourier transform. As I say, we'll find it very useful to think about the evolution of the inhomogeneous field in terms of the evolution of individual Fourier modes, individual waves with a characteristic scale k. And in particular, it allows us to describe, for example, quantities such as statistical properties of the distribution, such as the power spectrum that I've already talked about. So as I said, the theory will describe the statistical properties of the distribution. So we're assuming some statistical representation. For example, that the amplitude of the density in linear theory we'll assume has a Gaussian distribution. So it will have some mean and some variance, but then the distribution around that will be defined by a Gaussian or a normal distribution. We'll assume indeed that that distribution is isotropic because as far as we can see, there are no preferred directions, spatial directions in the cosmos. And so with our theory, we'll make predictions for the quantities such as the average of that distribution, that ensemble of all possible outcomes. And as I said earlier, we have to contrast that with what we see from observations, which is just one realization of this distribution. So we're imagining that our universe, the precise distribution of structure, of matter, and therefore structure in our universe could have been different. We may be able to discover characteristic scales, but there won't be preferred directions or preferred places in the universe. We'll simply get a distribution we'll make predictions for the distribution of the average density or the average variance power variation on different scales. But then what we get to see when we observe our universe is the outcome of one of these random experiments. So we think of the actual universe we see as being drawn at random from all the possible realizations. So, and this is sort of, motivated again. Well, there's two ways of thinking why this might be the case. I will tend to think of models for the origin of structure, such as inflation or primordial bouncing cosmologies, where we see the origin of structure as coming from quantum fluctuations. So indeed, the universe we observe is the outcome of a quantum experiment where the precise hot and cold spots on the cosmic microwave background sky, for example, are really drawn randomly by the outcome of an observation of a quantum system. I mean, another way it could be is that there could be some, other models for the origin of structure. People in the past have speculated that there's some complex microscopic physics. So the randomness could simply be the result of complexity on some small scale. Nonetheless, if it's too complex to be predictable on the small scale, the outcome would essentially be random as to what we see on for the structure in different parts of the universe. But then we make these theoretical predictions and we then compare them against the one cosmic microwave background sky that we see. It doesn't change, it's always the same, and we can map it as well as we can, but we'll only ever see the outcome of our universe and how it is on the large scales around us. So we're making this sort of a comparison between these two, as I say, interpreting the observations we see as being one outcome of the statistical distribution that we describe in theory. I hope I haven't made that sound too mysterious. It's just, as I say, the theory makes predictions for a distribution, and then the observations are just one realization drawn from that distribution, and we can see if that is consistent with the theoretical models that we've made. So as I say, the sort of theoretical predictions we would make would be something like the power spectrum. So this would be is defined as being the correlation between two modes in Fourier space, delta rho of K1 and K2. And if you take the average properties of delta rho for K1 and correlated with multiplied by delta rho K2, that will in fact vanish for a Gaussian distribution unless K2 is actually equal to minus K1. So typically we'd be talking about the 2-point function in Fourier space, and if K2, so the correlation vanishes, so it's described by this delta function, Dirac delta function, K1 plus K2, it vanishes unless the sum is 0, and that delta function then appears with an amplitude, which is the power spectrum P, as a function of the wave number. And in fact, for an isotropic distribution, you can show that this power spectrum is indeed independent of angle. So it's just a function of the amplitude of the wave vector K1 or equivalently K2 that we have here. And that's why we can represent our theoretical prediction for a model such as this. It's shown in the, as I showed earlier, for the matter. This is the power spectrum for the distribution of matter inferred in our universe. And the theoretical curve here is a black line that indeed we can compare with the observations of the estimates of the power in our universe on different scales. Okay. So that's the Fourier space 2-point correlation function, the power spectrum. From that, for example, we can construct the variance in real space. So the expectation of delta rho squared in real space, and we can do that by simply substituting in for delta rho at each point x in terms of the Fourier decomposition that I've just showed. So you can see I've substituted in here for delta rho at K1 with the dependence e to the I K1x, and delta rho K2 with a similar e to the I Kx dependence, and integrating over both of those using the definition of the power spectrum as given above, means that we can use the Dirac delta function to do one of these integrals. And we see that the variance in real space then comes from an integral over the power spectrum in Fourier space, in K space, we often say. And if you think of this as an integral over a range in log K, remember the power spectrum here is independent of the direction of K1 here. So in fact, although this is a 3-dimensional integral, it's there's just a factor of 4 pi that comes from integrating over all the angles, and then we're left with an integral over the wave number dk. So this is actually an integral of what I've written here is calligraphic P, the dimensionless power spectrum P of rho, and you integrate that, and the power in each interval, in logarithmic interval and wave number, is what we call the dimensionless power spectrum. So the variance in real space is the integral over log K of the dimensionless power spectrum curly pk here, which is different from this original definition of the power spectrum in Fourier space p rho, and it differs by a factor of, well, essentially a factor of k cubed, up to factors of 2 pi. So, and for example, a scale invariant power spectrum we think of as being a power spectrum which gives a variance which is independent of the wave number k. So it would be the dimensionless power spectrum here, which is scale invariant for a dimensionless, for a scale invariant distribution. If we go beyond the linear theory, we can explore higher order statistics of the field. For example, the 3-point function in Fourier space, that would be the bispectrum, which would now be a function of 3 wave numbers. But the bispectrum again, for an homogeneous distribution, has to be a function, this correlation of K1, K2, K3 will vanish unless the sum is 0. And the bispectrum is then again the amplitude of the coefficient of that 3-point correlation in Fourier space. But for a Gaussian distribution, this is 0. In fact, the correlations of any odd number of perturbations is 0 for a Gaussian distribution. So as I said, we will take the first order perturbations to be Gaussian, so the bispectrum will vanish. And instead, we'd expect the bispectrum then to only appear actually at 4th order, where you get a contribution from if you're correlating delta rho at K1, K2, and K3, you would get a non-zero bispectrum, but only from the 2nd order contribution from 2nd order terms. Because remember, the 2nd order perturbation, delta 2 rho K1, for example, that will come from solving a differential equation which has a source term which is quadratic in the perturbations. So this first term would be quadratic, and then overall this would be the bispectrum would be a 4th order term in perturbation theory. So as I say, if we take the linear theory to be Gaussian, we'll have a 0 bispectrum. But a non-zero bispectrum, for example, and people have looked for this in the cosmic microwave background anisotropies, this would be evidence of some higher order terms playing a role in the perturbation theory. And certainly, for example, if you look at the effect of the lensing of the gravitate, we know that I showed the map of the weak lensing of the cosmic microwave background anisotropies. These are indeed only produced by these are higher order effects. And their statistics indeed are described by a non-Gaussian distribution. So there are non-Gaussianities in the observed temperature anisotropies of the cosmic microwave background. But that's due to lensing, gravitational lensing along the line of sight of the primordial anisotropies. And as far as we can tell at this point, the primordial anisotropies in the cosmic microwave background are perfectly well described by a Gaussian, effectively Gaussian distribution of temperature anisotropies. But one of the goals of future CMB experiments, and indeed large-scale structure experiments studying the distribution of galaxies, is to look for evidence of some primordial non-Gaussianity, some non-Gaussianity that exists even at the earliest times before the last scattering of the cosmic microwave background. That would be could be some signature of nonlinear physics in the origin of the perturbations, for example, during inflation, or some alternative model for the origin of structure. The fact that we see no such primordial non-Gaussianity at the moment suggests that indeed, as far as we can tell, the origin models would be well described by some weakly coupled quantum field, because there's no evidence yet of nonlinear interactions in those fields at very early times. Okay, so that's really the introduction to the higher order statistics. I was going to say, so far I've talked really about density as my example of a fluctuation, a scalar quantity that has inhomogeneous fluctuations. I could finish off by talking a little bit about vector and tensor type perturbations. I think I've probably been talking for an hour and a half already. If I've got 5 or 10 minutes more, shall I go on and talk about just vector and tensor perturbations briefly? before finishing the lecture?
You had started about 7 odd minutes earlier. You
Yeah.
have 10 minutes left. You can go on.
Okay. So let me just finish by going beyond talking about simply a scalar quantity like density. So density, of course, is just or pressure. These are scalar quantities described by a single number at any point in space-time. But already to model the density, we need to know, as we're showing from the sort of typical continuity equation, the density will change partly because you've got a fluid flow, velocity flow into or out of different regions in space-time. So we also need to model vector quantities such as velocity. And here, a vector at any given point in space-time obviously has, in three-dimensional space, has 3 components, but we'll find it useful to decompose those 3 degrees of freedom into one part that is derived from the gradient of a scalar. So this is, so we'll refer confusingly perhaps, we'll talk about the velocity as having a scalar component, which is represented here as the gradient of a vector velocity potential V, Vs. And that's a natural thing to do in fluid flow. You would describe this as a potential flow or a longitudinal flow, which is, let's say, simply in the simplest example here shown on the left-hand side, this would be perhaps a flow out from a source point, or a flow into a sink. So this is a simple kind of vector flow that's derived simply from the gradient of a potential, a scalar potential, which we'll call Vs. And characteristically, if you calculate the vorticity of this, here in the bottom row here, I show the vorticity of that flow. Well, it vanishes because, of course, if you take the curl of a gradient, you get 0. So one component of the velocity flow will be this kind of a scalar potential flow. But then there are 2 other components, and they are the 2 transverse or divergence-free flows. So these are what we call true vector perturbations. They can't be just derived from the gradient of a scalar. And indeed, if you take the gradient of this vorticity, VV, then the gradient of this vanishes. So, and there are, because it's transverse, there's 2 components to this vector flow. So in general, a flow will be composed of a sum of both a potential flow and a transverse vorticity or vector flow. As I say, the divergence of the vector vanishes and the curl of the scalar flow vanishes. So we can distinguish, these are again independent components of the flow. So and this is useful to make this decomposition precisely because it's the scalar flow, or it's only the potential flow that couples to the scalar quantities such as the density. So if you remember when we looked at the continuity equation for the density perturbation, it was sourced by the divergence of the velocity, and that would vanish for the vector flow. But the scalar flow, the potential flow, does contribute here. So it will simplify our equations that we can treat the scalar and the potential contributions to the vector flow in their evolution. They evolve independently in linear perturbation theory. But again, at higher order, they become coupled. So at higher order because we get the products of quantities such as the density and the potential, the product of two inhomogeneous quantities, even if one is a vector and even if these are both the scalar components, they can source a vector term at higher order. And so indeed, we'll often make the assumption that the vector perturbations are zero at first order, but even if we set them to zero at first order, which we can do consistently, at second order, we must consider the vector component of the velocity flow. When just to extend what we're saying about Fourier transformations, you can perform a Fourier transformation of both the vector and the scalar part of the flows, velocity flows. So the scalar part is simply, as you'd expect, a Fourier transform of the scalar Vs. And of course, if we then construct a flow from that, the gradient of this scalar in Fourier space, taking a spatial derivative here, d by dx basically brings down a factor of ik. So we see that this is the Fourier transform of the vector part, the velocity, the scalar part of the flow. Whereas and it's, as you would expect, this is why it's longitudinal, because this vector points along the wave vector k. Whereas for the vector part of the flow, it's decomposed into two transverse polarizations, which we call E, and I've called E and E tilde here. And these are polarization vectors defined to be, I've tried to sketch it here, E and E tilde are the unit vectors orthogonal to the wave vector k here. So as you'd expect, the Fourier transform of this, the flow here, has one longitudinal component, that's the scalar component, and two transverse components, those are the vector components, and their amplitudes here are v and v tilde for the vector components. So the general flow comes from the sum or the integral over all those possible waves with e to the ikx dependence with longitudinal and two transverse vector components. So as you'd expect, the vector has three components, one coupled to the scalar perturbations and two intrinsically vector perturbations here. And we can evolve them independently. And finally, then we can do a similar thing with, so a vector flow is a one index quantity. Once we start, in particular, when we talk about metric perturbations, we'll need to consider two index quantities, tensor quantities, three tensor. But similarly, a three tensor, and for example, a spatial metric perturbation, can be constructed from scalars. So you can have a conformal factor C times the spatial metric in flat space, that's just the Kronecker delta ij. You can also construct a two index tensor, which from two spatial derivatives of a scalar. So two components of this tensor perturbation are in fact derived from scalars. So 2 degrees of freedom in this three tensor are what we'll call scalar perturbations, C and S. So we can have scalar metric perturbations, for example. You can also have vector metric perturbations because you can construct a three tensor. So Tij here is a symmetric three tensor. So we can construct it from symmetric derivatives of a vector, three vector. So so we'll have two components here associated with the two polarizations of the three vector V. And then what remains and these are really what we call the tensor perturbations of the metric, for example, will be remaining perturbations which can't be derived from scalar or vector perturbations. So these are transverse and trace-free tensor perturbations. And those will be the, as we'll see in the metric, those will be the free gravitational wave perturbations of the metric that cannot be constructed from scalars or vectors. So they're intrinsically tensor perturbations of the metric. And therefore, to construct these, we again have polarization tensors. Typically, we can construct these in terms of the so-called plus and minus and cross perturbations, polarizations. Actually, you can construct these from the same orthogonal transverse vectors E and E tilde. So the plus has this combination of distortions along the E and opposite EI, EJ perturbations, and with the E tilde minus E tilde I, E tilde J. So these represent distortions along the E and E tilde directions. The cross is this mixed product of the two vectors, so distortions at 45 degrees actually to the E plus configuration. And these are transverse because they're orthogonal to the wave vector K by the definition of the polarization vectors E and E tilde, and they're also trace-free by construction. So these are in Fourier, how you represent in Fourier space, the transverse and trace-free distortions of the metric. You use the polarization vectors, and then each of those components has an amplitude, a time-dependent amplitude, little h, k in each direction k, either with the plus or for the minus. So two independent amplitudes for the two independent polarizations of the tensors. Okay, and that's really where I'll end up for today. Sorry, I've now taken more than my 10 minutes. But these will be the building blocks which we'll use tomorrow to really model the metric perturbations. And this is where the origin of the scalar, vector, and tensor decomposition that we use for metric perturbations comes. These definitions and decompositions into the different components. So I will finish there. I had lots of slides I could have gone through if I had time, but I've got time to go through them tomorrow. For now, that's the end of my first lecture. If we've got time, I'm happy to take questions if we have time for that. I know we have a tutorial session later today that I'll be back online for.
Thank you, David. Maybe we can, have one or two questions. Yeah, please go ahead.
So we started with the linear perturbation equation, that is delta rho Tx. So we have to solve that equation. So what are the initial conditions to solve that equation, and how one get that initial condition to solve?
Right.
That?
Well, indeed, I haven't. I haven't attempted to solve those equations yet. We'll look at them later. I'm just looking for if we have. I mean, if we. Yeah, you're right, absolutely. So here's an example where I was sort of giving a linear differential equation for the density. In the standard hot Big Bang cosmological model, we need to indeed specify any differential equation, you need to specify the initial conditions. There's no there really is no way in the standard hot Big Bang cosmology to specify these initial conditions. They start, you have to set up the density on very large scales. We know already that there are perturbations seen in the cosmic microwave background on the largest scales that we can probe. Already on the scale of our observable universe, these perturbations exist. with some characteristic amplitude even before the last scattering of the cosmic microwave background. So that's where we look to models such as cosmic inflation to set the initial conditions. And what we'll see is that you get in the standard cosmology, there's the initial density fluctuations are naturally described by a characteristic metric perturbation, a curvature perturbation at the level of about 1 part in 10 to the 5. But as I say, in the standard cosmology, you just have to be given. you are not it's an initial condition that's not provided by the model. In an extension of the standard cosmology, such as inflation or perhaps bouncing cosmologies, the challenge indeed is to make a prediction for what those initial conditions should be. And they appear to come in, saying from inflation, they would come from quantum fluctuations of a field in its vacuum state. So this is a very appealing idea that they could be simply the 0-point fluctuations of a quantum field.
And that Gaussian distribution you talked about, so that's just an assumption, a statistical assumption to start with. So
yeah.
That related to any initial condition or something like that?
Yes, so it is exactly it's the statistical properties of the initial conditions that you need to you need to supply in the standard cosmology. So for example, in the 1970s, Jim Peebles, Zeldovich and others speculated about what might be the initial conditions for the hot Big Bang cosmology. And indeed, they assumed there was an assumption for simplicity that they had a Gaussian distribution, because you didn't know, if you don't know, it's the minimum, a Gaussian distribution has the minimal information. All you need is to specify the power spectrum. And so that is what they assumed. But it was an assumption in the 1970s, and it was really only in the 1980s that when inflation was proposed, that people had an idea, gave a fundamental reason why it should be a Gaussian distribution, because the 0-point fluctuations of a quantum field, they obey a Gaussian statistics. So that could be the fundamental reason. And there's a lot of interest in trying to establish if that really is the case.
Go ahead, please.
Yeah, how do you define density, let's say, for dark matter here?
Well, so density, yes. So indeed, I have talked, I will probably in my lectures largely talk about, imagine a fluid, but it's true if you're thinking that dark matter actually is particles. And so what happens, of course, if you have a collection of particles, you need to define the density on a scale. So indeed, when I was talking about, for example, the variance of the density field, that is the typical amplitude of fluctuations in the density field at different points in space, you have to define a smoothing length, which I haven't done. You notice my Fourier integrals here. I've conveniently not told you what the upper and the lower limits are of my Fourier distribution, but indeed there's a smoothing implicitly. One does, for any particular set of observations, one needs to define a smoothing length, and that sets the upper limits on the Fourier range, the range of wave numbers. Yes. So yes, you can't, below, for example, the distribution of galaxies, these are very big objects. So it doesn't make much sense to talk about the density of galaxies on kilometer scales, because galaxies are are kiloparsecs in scale. So yeah, that you need to define the density, the average density in a sphere, for example.
Maybe there are actually a few more questions from the participants here. Maybe we can take them in the evening session during the tutorial session.
Yes.
I can just see whether there is one question from the online participants which we can take. Are there any raised hands, Gopi? Can you help me with it? Okay. I don't see any raised hands and questions amongst.
I can see one raised hand. Neil Shah.
Okay. Yes, Neil Shah. Yes.
Hello, I had a question about the order by order expansion of the perturbations in terms of epsilon.
Yeah.
Is this a Taylor expansion?
Yes, so in effect, that's right. You can think of this as a Taylor expansion. So here, you're perturbing about a background value, and yes, I mean, so it's a mathematical construction where you're introducing this order parameter. But you're right. The way you handle this is exactly as you handle a Taylor expansion. But as you can see, it's a way of then defining a linear perturbation and solving for these linear terms before you then go and solve for the higher order terms. But the result that you're getting here is exactly the same as if you were multiplying together, for example, the Taylor expansion of rho and v here.
Okay, so here we haven't defined epsilon like explicitly, like except requiring it to be small, right?
Yeah, so we require it to be small. That's right. And so it's for this to be useful. I mean, we tend to work in the limits. Indeed, formally, you're expanding about a sort of infinitesimal parameter, epsilon, and yeah, in order for these to be, because they're formally defined in terms, indeed, just like the Taylor expansion, they're defined about some point in the background. Here it's the background solution.
Okay, thank you.
Yeah.
I had a small question about the very first slide this time.
That's the very first slide, did you say?
Yes.
Oh, what was that? Oh, the history of the universe, you mean?
Yeah.
Yes.
Yes. So I just wanted to know, where would the primordial gravitational waves be? Where would they fit in this picture?
Oh yeah, very good. Yeah. So so indeed, so the importance of the cosmic microwave background surface here is that's the point at which the universe becomes transparent to electromagnetic radiation. So at the present day, we don't imagine that we can see anything beyond this, the last scattering surface of the cosmic microwave background in electromagnetic radiation. But to go beyond that, if we wanted to really see the early universe at earlier times, well, there's neutrinos possibly, which last scatter around about the epoch of nuclear synthesis. But gravitational waves could indeed, in principle, allow us to see directly back to, well, the universe is transparent to gravitational waves throughout this epoch. So, I mean, it's possible that, I mean, people are interested, for example, in whether you could see information about the possible quark hadron phase transition, for example. What's that, 10 to the minus 4 seconds here through if there's a first order, if there was a strong inhomogeneities in the plasma that could emit gravitational waves. So indeed, I guess Danny Figueira, I should say, is going to talk about this in his lecture course. But you could see back to this epoch possibly. In principle, you can see right the way back. Possibly, in the Planck epoch is literally the point at which the gravitational waves would be strongly coupled. So pretty much any classical physics, the universe is transparent to gravitational waves. So inflation itself, if indeed that is the correct model for the origin of structure in the universe, would it itself emit gravitational waves? And we could see directly back to that in principle with direct detection of gravitational waves. If you're sensitive enough, if your detectors are sensitive enough, and if there's not some loud interfering signal at lower redshift. So for example, binary black hole collisions in the nearby universe are a wonderful signal, produce a wonderful signal of gravitational waves, but they would also stop us from seeing a primordial signal because if there's too much in the way of sort of foreground signals. So yes, gravitational waves in principle could see anything on this, anything up to the Big Bang in this picture.
Thank you, David. Thank you, Neil, for the question. There are a few questions here, David, but as I said, we can take it in the evening in the session.
Yeah.
Thank you very much. We'll see you in a few hours.
That's good. I will be back online in a few hours. Yeah.